Welcome back to DATQVAULT video lectures. We're continuing our lectures on conformational analysis. In this lecture, we're actually going to look at the conformation of ring systems. So the conformation of ring systems actually deviate quite a bit from the conformation of a linear system. And like the last lecture, we looked at the conformation using Newman projections, and that is really useful for linear molecules in trying to tell the different energy states of molecules in different conformations of linear systems. But cyclic systems, it's a little bit harder to do that. And that's because you can't really rotate freely around a single bond in a ring system because everything is strapped back into a cyclic form. So when we're looking at ring systems, here's an example of a cyclohexane. We usually see it drawn out as a flat planar ring. But in reality, cyclohexane 99.99% of the time does not exist in a planar form like this. And that's because bond angles in a planar cyclohexane are actually 120 degrees. So if you remember, the most stable conformation for any tetrahedral center, which of course you find in a cyclohexane ring, is 109 degrees, or 109.5 degrees rather, in this tetrahedron that I have drawn here, where the center is of course a carbon atom. So how do we actually make a cyclohexane ring achieve a tetrahedral shape? And we do that by actually bending it. In this case, it's bent into kind of what's called a boat form, and that's because it kind of, sorry, not a boat form, rather a chair form, because it resembles a chair. So once you bend a cyclohexane ring into this form by lifting up one of the carbons and lowering another carbon to get this structure, you actually relieve a lot of what's called ring strain or angle strain in the molecule, going from 120 degrees down to the 109.5 degrees, which is what a tetrahedral center prefers to be in. So now that we know what the shape is of a cyclohexane ring in its most stable form, we can actually start putting substituents on it and then start studying how the different placement of substituents around the cyclohexane ring affects the conformational energy of the overall molecule itself. So when placing substituents on a cyclohexane ring, there's basically two distinct orientations that the substituents take, and that's either an axial orientation or an equatorial orientation. So when we see a cyclohexane drawn out in a planar form, we imagine it looking something like this, where one of the hydrogens, in this case, is back, and the other hydrogen is forward. But that's not really the way it looks like in 3 dimensions. We want to make it look like an actual tetrahedron, which looks something like this. So if you try to convert this shape to this one, you can actually see in the cyclohexane model each of these sticks coming off being a substituent. That this structure here, this tetrahedron structure, very closely represents this structure right here, which is one of the carbons on the cyclohexane. And if you notice, it directly looks like a tetrahedron. So you can see the bond angles here are 109.5 degrees, which is the same for any bond angle in a tetrahedron shape. And so this is why this conformation greatly lowers the energy of the cyclohexane. So when looking at the different substituents, I told you that there are axial and equatorial substituents on a cyclohexane ring. Here I have the structure kind of highlighting all the axial substituents on the cyclohexane. What's important to know about the axial substituents on a cyclohexane ring is that they are all able to interact with one another. And then the rest of the substituents facing out and away from the ring are called equatorial substituents. So these guys are axial, meaning they're straight up and down, and then equatorial, meaning they're pointed away from the ring. typically substituents that are put in the equatorial position don't interact with any other substituent because they're out and away from anything else in the molecule. So typically when you want to have the lowest energy state of a cyclohexane ring, the substituent, the largest substituents, will be in the equatorial position, pointed out and away from any other substituent, which greatly decreases steric repulsion. Alright, so now that we know how substituents are placed around a cyclohexane, let's try our hand at actually drawing different substituents on a cyclohexane ring. So here I have an example of dimethyl cyclohexane, 1,2-dimethyl cyclohexane, this being the 1 carbon and the 2 carbon in each case. If you notice, you can have different stereo chemical conformations in a cyclohexane. You can have like a methyl group, in this case, pointed back and one of them pointed forward, or both of them pointed forward, or both of them pointed back. If one of the substituents is back and one is forward, we call that a trans orientation, meaning they're on opposite sides of the cyclohexane ring. When both substituents are faced in the same direction on a ring, we call that the cis orientation, cis standing for them being on the same side of the cyclohexane. So when looking at the planar structures, it's kind of hard to tell the orientation of these substituents. So to better visualize them, to better visualize the energetics of the entire system, we should draw it out in a three-dimensional chair form. So how do we actually place these substituents correctly on a cyclohexane chair? So if we notice this substituent, this methyl group, is faced back, we want to pick a substituent on the cyclohexane ring that is actually faced back and away. So here I have highlighted all the substituents that are faced up, and then the other half of the substituents, which are not highlighted in bold, are faced back. So this makes it easy to see which substituents are actually facing up and which ones are facing down. So if we arbitrarily number one of these carbons 1 and number the other one 2, we can place this methyl group on the 1 carbon, but we want to be facing back, so we're going to place it down here. The other methyl group, we want it to face up, so we're going to put it on the number 2 carbon that is facing up and away from the other methyl group. So here I've placed these 2 methyl groups both in the trans orientation, but as you can see, there's actually another orientation that we can place these methyl groups to also get a trans orientation. So if we re-bring up a fresh cyclohexane ring, we can make this the 1 carbon, and we can make this the 2 carbon. Notice in the previous example, both of the methyl groups were in the equatorial position. If I make this the number 1 carbon, and I put the methyl group back, the methyl group is now in the axial position. And if we want to make this methyl group facing up, we're going to choose the other axial position for the methyl group to make the overall molecule the trans orientation. So in this case, both of the methyl groups are now in the axial position, and they're able to interact with all of the other substituents in the system, being hydrogens. And so this molecule actually has a higher energy than if the methyl groups were both in the axial position. Alright, so let's take a look at the cis cyclohexane over here. So if we make this the 1 carbon and this the 2 carbon, we want them to both be facing up and towards us. So we'll put a methyl group here in the up position, and we'll put another methyl group here in the equatorial position facing up. So unlike this model over here, if we made this the number 1 carbon and this the number 2 carbon, and we place these in the up positions, we again get 1 methyl group in the axial and 1 in the equatorial. So there's only 1 orientation for the 1,2-dimethyl cyclohexane cis model, and so there's only going to be 1 energy state for this molecule. All right, so let's move on to a question. So here we're asked to draw all the conformations of 1,4-dibromo cyclohexane and determine which conformation is the most stable and which conformation is the least stable. So take a second, draw out the possible chair conformations of 1,4-dibromo cyclohexane, and label one as the most and one as the least stable. Alright, so the first thing I would do to tackle this problem is to actually draw out planar form of 1,4-dibromo cyclohexane. And then we can start drawing our chairs, and then putting the bromines in orientations that are different at the 1 and the 4 position. Alright, so here is a chair that already has all the substituents placed on it, so I can just throw a couple of bromines on here. If we look at the number 1 carbon, which is this one, make this one the number 4 carbon, we can put a bromine here arbitrarily, and we can put a bromine at this position arbitrarily. So this conformation is going to be, of course, a cis conformation because both of the bromines are facing up, one of them axial and one of them equatorial. Another possible conformation is for both of the bromines to be in an axial conformation. This particular one is going to be trans because the bromines are on opposite sides of the cyclohexane. And then the last conformation that we can draw are both of the bromines in the equatorial position on the cyclohexane ring. So if we remember from a few slides earlier, substituents that are in the equatorial position make the molecule more stable because they're faced out and away from the ring and they're not interacting with anything sterically. So this being a trans molecule, both of the bromines are faced out and away in the equatorial position. So this conformation is actually going to be the most stable for 1,4-dibromo cyclohexane. Both of the bromines in the axial position, they're sterically interacting with all the other axial substituents. So this one is going to be the least stable out of the 3 different possible conformations of 1,4-dibromo cyclohexane. And of course, one in equatorial and one in axial. This would be, of course, right in the middle energetically between these two systems. Alright, so now we're going to look at the difference between a chair and a boat conformation. So we talked about the chair conformation being the most stable cyclohexane conformation, but we can actually take this flap of the chair, and if we move it up, we'll actually get what is called a boat conformation of a cyclohexane ring. This energetically is one of the highest energy states of a cyclohexane ring. And then if we bring this flap down on this side, we're going to get the cyclohexane ring back again. But if you notice, it's going to be completely flipped around. So this is what's called doing a chair flip or a ring flip of a cyclohexane. It's not simply taking the molecule and flipping it over. It's actually taking one flap and bringing it up, and the other flap and bringing it down. It's not the same thing as flipping the molecule over because all the axial substituents then become equatorial, and all the equatorial substituents become axial. So you're completely, basically, inverting the configuration of the overall molecule. And so a really easy way to visualize it is to take all the axial substituents on the cyclohexane ring, and then if you take and you flip up this flap on the ring, you'll notice that all these substituents become axial, and now we have a boat conformation right here. And if we take this flap and we fold it down, all the substituents then become axial. So we go from, if we had a methyl group over here, a lower conformation, energy conformation, now to the methyl group being axial, and now we have a higher energy conformation. Alright, so why exactly are chair conformations a lower energy state than a boat conformation of a cyclohexane? And an easy way to visualize that is using a Newman projection. So if we take and we look down these two carbons, carbon 1 and carbon 2 on either side. This is our eyeball right here. We're going to be looking down this carbon and this carbon right here at the same time. And what we see is actually this right here for a Newman projection, which is called kind of a double barrel projection, if you will, because we're looking sighting down two carbons at the same time. And if you notice, in the chair conformation of the cyclohexane, all of the substituents are actually ghost to one another, which makes the energy state of a cyclohexane ring very low. But if we're to actually look at the Newman projection of the boat conformation of a cyclohexane ring, this being the 1,2 carbon, 1 and 2 carbon, we're going to look down the same carbons in the boat conformation, and if we look at the Newman projection of that, we'll notice that everything is actually completely eclipsed. So really what we did to get from, if we remember how to get from a boat conformation to a chair conformation, we take this flap and we will rotate it up, and basically you're taking this carbon and you're rotating it in an upward position, and that actually rotates this carbon this direction, and it's going to rotate this hydrogen this direction, giving us this structure down here. So this is why a boat conformation has such a higher energy state than a chair conformation, is because all the substituents are eclipsed. So if you're ever asked a question on the DAT, which conformation is most stable, you can always cross out the boat conformations because they're always going to be of higher energy state than the chair conformations. And then if you're asked to differentiate between energy states of two cyclohexane molecules, you'll always go for the conformation where the largest substituents are always in the equatorial position and not in the axial position, because the equatorial position you have less steric hindrance or less steric interaction between those substituents. Alright, with that said, let's quickly do a practice problem. This problem, similar to one you will see on the DAT, is asking for the most stable conformation of 1,3-dichlorocyclohexane. So you have 5 options. So why don't you pause the video, pick out the most stable conformation, and then we'll work through it together. Alright, so let's work through this sample problem. Here I have what you'll most likely have on the DAT is just a completely just a dry erase marker board over here on the right hand side. Since the exam's computerized, you're not able to draw on the computer, so we're just going to again do a process of elimination kind of deal. So like I said a few seconds ago, all the boat conformations are going to be the highest energy conformation, so we can quickly cross those out, and that leaves us with just the chair conformations remaining as the lowest energy state conformation. So we're going to want to look for the conformation that has the lowest energy state between all these 3 chairs, and if you remember, anything in the axial position is going to be a higher energy state than anything in an equatorial position. So here we have a diaxial interaction here between these 2 chlorines. That creates a lot of energy strain in the molecule, so we're going to initially cross that one out. Here we have an axial and an equatorial substituent, and here we have 2 equatorial substituents. So the more equatorial substituents we have, for the largest substituents, the lowest energy the molecule is going to be. So we're going to go with answer B as being the most stable because, number 1, it's in the chair conformation, and 2, the 2 largest substituents on the molecule, being chlorines, are both in the axial position. Alright, so I'll suggest that you go through and do a lot of practice problems containing cyclohexane rings and different energy states to solidify everything you kind of learned in this lecture. And then I hope to see you back for the next lecture.